thank you for the invitation to speak, and I'll talk about bootstrap percolation. This is joint work with Rob Morris, who's at IMPA. So it's slightly old work, which I chose because it's very nice to present very quickly, because you can present it very quickly, and it's very hard to prove, so you won't get the suffering. You'll only get a result. So what's this bootstrap percolation thing? You start with a graph, which in our case will be the grid n by n. You put a percolation on the vertices, so each vertex is initially infected with probability p independently. And then you perform, that's all the probability there is to this. So afterwards you perform a totally deterministic dynamics, which is the following. Infected vertices remain infected, and if you have at least 2 infected neighbors, you also become infected. And then you iterate this. So this is what it gives. So now you see that these 3 people at the top are stuck already. They won't do anything on the next step. But the guys at the bottom are trying to grow to fill a rectangle. So that's what the process really actually does. But then the 2 rectangles actually are too close together, so they meet and they merge to form a bigger rectangle. And that's how it grows. And in this case, it will infect everything. So we call the closure the closure. So the thing that you get in the end. We say there is percolation if the closure is everything. And we define the critical probability, which is the value of the parameter p, for which percolation will start becoming probable. So you have this standard picture that so this is the probability of percolation. And here you have p. You have some function which is like this. Okay, and so this is 1/2, and this thing is pc of n. And this is for every n. You have a different picture, and you want to know what happens when n is big. Okay. So just a bit of motivation before I continue. This is really the most original bootstrap percolation model. Now there's lots of them introduced in the 70s to model magnets in certain conditions. Okay, it's central to recent classification that unifies the domain somehow. My personal motivation are kinetically constrained models, which are interacting particle systems that I won't have the time to talk about. It's related to Ising. You can think of this as spread of whatsoever on whatsoever, so it's quite universal model. Okay, the last one is the most important. Right, so let me tell you a bit about what's known along the line of research that I'll talk about. I'll jump over Van Enter and Schonman directly to the most fundamental paper in bootstrap percolation, I would say, which is by Eisenman-Lebowitz. It's somewhat the first important one. Okay, I'm abusing. So that they give the order of PC. In particular, PC of n will go to 0, which was already known. But they determine the order of PC. And I'll give you a proof of that. It's not hard, but it introduces many very important things. So the upper bound, what we need to do is give a sufficiently likely construction of something which will percolate. That's what we need to do. So how we do that? Well, you imagine that you live in n by n grid, n is super large, and I will ask inside at some particular position, if I fix a square which is 1 over p times 1 over p, I'll ask for the following event to happen. So I want to have an infection here, then I want to have an infection here and here. So this thing allows me to infect this. Then I want to have an infection on this line and on this column, then on this line and this column, and so on. And this allows me to infect everything, right? And you can calculate the probability of this, and it's just exponential minus 1 over p, roughly. So if my n by n thing is, if n is exponential 1 over p, this will happen somewhere in the whole domain. And you can easily compute, it's essentially the same calculation that leads to that if you manage to infect all of this, it's just likely to grow and infect everything. So that's what gives you the upper bound. The lower bound is based on what we already observed on the example, so these rectangles merging. So just notice that in this rectangle merging process, if you have two rectangles which merge, the rectangle that you get is at most twice as big as the bigger one. Okay, you see that? Where big is in the sense of long side or, okay, in an appropriate sense. And in particular, if I start out with just single sides, so small things, and I end up with the huge n by n rectangle, square, it means that at some point I passed through something which had roughly size 1 over p, up to a factor 2. So that's the same bottleneck as before. So how do I bound the probability of, each rectangle that you see in the rectangles merging process is infected only from infections which are inside it. It's easy to see. So how do I bound the probability of one of those rectangles being internally filled, so being infected from the inside? Well, I just say, oh, if there are two consecutive lines that have no infections, it won't get infected entirely. Okay, if you imagine that here I have two lines of non-infected vertices, okay, even if I infect everything else, they stay separated. You calculate the probability of this event happening, which is very easy, and you get this result. Okay, 15 years later came a breakthrough of Holroyd, really, who determined the constant, which turns out to be pi squared over 18, which is just some integral happens to have a nice value, but we would be just as happy with 0.5 something. And the important thing is that he really introduced a lot of new techniques to the domain to prove that. I'll tell you a tiny bit about it. The upper bound is easy. In general, upper bounds on this are easy because it's just a construction. So what changes with respect to what I have here is that, so you don't grow one line at a time. If you imagine that you've already grown up to here, you'll ask for this thing to grow up to here with a distance which is, okay, with the distance which is 1 over root p, and then you'll switch sides. And then you'll grow this way. And when growing one way, you don't ask for an infection on every line. You ask for at least one infection in every 2 lines consecutive, which is a bit better. And it's sufficiently good to give you the right constant there. So that's the upper bound. The lower bound is much more tricky. The most important two things that Holroyd introduced are hierarchies. So hierarchies are an encoding of the rectangles merging process, which sort of naturally gives you a tree, a binary tree. If you think of two rectangles merging, well, okay, you have two nodes of your tree that merge, and then you continue. So you want to look at this tree and do a union bound on the trees labeled with rectangles. Now, that would be way too bad because there are tons of trees. But what he did is, okay, we won't start from the very small sites, from the leaves of the tree. We'll start from fairly big rectangles, and we'll grow in big steps. So there's two things. You want to not see very small rectangles in your hierarchy. And if you have a rectangle which is big and it merges with a sort of small rectangle, you don't really want to see that in your hierarchy. So if you have such an event occurring, you want to say, okay, this big rectangle, after several steps, it becomes slightly bigger but I don't really tell you exactly how. So I don't tell you exactly how it merged. So that you can encode in a tree which is not binary, but it can have unary nodes as well. Okay, and the other very important thing that he noticed was that if you have two rectangles merging in the process, their internal filling occurs disjointly. And for those of you who know what that means, it allows you to apply BK inequality, which is very useful for lower bounds. Right. And okay, lots of other ideas that I won't have the time to talk about. Now, yeah, you may be tempted to say that this is the end of the story, which it isn't. I mean, there's lots of space on the slide. So why not? Now, I need to tell you about what's called the bootstrap percolation paradox. So from the very beginning, from the 70s and 80s especially, and okay, until not so long ago, physicists tended to do simulations to okay, estimate this constant or other things. And actually, every theorem on this list, essentially, was a disproof of what simulations predicted. Each time, really. I mean, I'm not aware of a good prediction based on simulation on these things. So why? Why? For example, this here, the prediction was about a factor of 2 off, more than 2. And they had a plus 1% or something, whatever. So why? And Grabner and Holroyd came up with the slow convergence theorem. So they say the convergence is at least like root log n. So you need to wait a lot to get the right thing. Now, this is an upper bound, so I'll tell you how it works. Essentially here, instead of when you work 1 over root p, you don't fix 1 over root p, but you allow an arbitrary choice up to 1 over root p, and okay, you're a bit more careful, and you manage to get that thing out of the entropy that you gain here. Okay, what was much more subtle was this lower bound, which is almost matching. Here you see the same 3/2 exponent, but you don't see a 1 on the top. So this was much harder. The main difficulty was that, again, if you want to prove such a bound, you are obliged to work with much finer hierarchies than Holroyd's, which implies that you have lots of hierarchies. So you have, again, this problem that you can't do your union bound, so you're stuck, but they came up with a way to come around that. So most of the hierarchies actually, why do you have many trees? Well, most trees actually have many leaves, and that's what gives you many choices each time. If you're going just straight, you don't have so many. But actually, leaves are the things that cost. So they managed to counterbalance that. I won't have the time to tell more about that. Okay, I'll skip that one. This one was at the same time as Holroyd's paper. By Balog and Bolobash. So they proved that the window, the critical window, something like this on this picture, is at most 1 over log squared. So it's actually much smaller than the precision. So it's much tighter than the precision we have on PC. So actually the convergence of PC is slower than the window, which sort of explains this thing. So if you look just at the profile, you have a sharper window, but the PC hasn't converged yet. And the proof is by what's now standard Boolean Fourier analysis by Ferdinand. Okay, I'll skip this one as well. Right, so here comes our result, which states that, okay, what you would hope is true. So the upper bound of Grabner and Holroyd is sharp. So we actually proved the lower bound. As I guess my time is just about over, I'll not talk about the proof. I'll just tell you 2 things. Okay, it's very, very technical, but two very, very important things that we need to take care of is using non-increasing and non-disjointly occurring events for our hierarchies, which you can imagine is a problem. But I honestly think that this is very much necessary if you want to get a bound which is sufficiently sharp. And the second thing is that we need to prove a very, very tight estimate on the probability of, if you have already a big rectangle and you want it to grow to a slightly larger rectangle, what's the probability of that happening? So this type of crossing, we have very tight bounds on that. Okay, and some other things that I won't talk about. So in conclusion, I'll leave you with these open questions, of course, and thank you for your attention.
Thank you, Ivailo. Are there any questions? Yes.
You said we use some non-increasing events.
Yes.
So, what kind of techniques do you use to evaluate these kind of things?
Yeah. So the events we use, you really have to use. The problem here is that what gives you many choices for your hierarchies are things of the type, I have many choices for where, if you imagine that I have this rectangle and this smaller rectangle, and I want to tell you exactly how I went from one to the other. So an intermediate step could be I grow by this way. But then I have sort of many choices here for up to where I go, which is what gives me this entropy problem. So the thing that you add to your hierarchy is you remember that I will go all the way that I can, which means that at the end of my rectangle here, I'll have what we call a buffer, an empty buffer, where I know there will not be an infection. So that's something which I have by the construction, but which I used to forget so as to have increasing events. So here we need to keep this, which helps you in several ways. So our events are essentially composed of two parts, which are increasing and decreasing, which happen on sort of disjoint on sort of disjoint sets of sites. And if you look at the right part of those, so you just take a part of your hierarchy on which you take the negative part. So you make sure that those happen on disjoint regions of your space, and you have disjoint occurrence of the decreasing and increasing ones. So technically, in the proof, I think we use Riemer's theorem, but it's really a weak type of Riemer theorem, because it's, I mean, for those types of events, I would be able to prove the Riemer theorem myself. But yeah, we use Riemer theorem, which, for those that don't know, is a generalization of BK to any type of event. Come again?
I can't hear you.
Without,
I'm sorry.
I think he asked if you can do without it, without Riemer's theorem.
Yeah. We could use BK. I mean, it's a stronger version of BK, which isn't as strong as the general Riemer theorem. So this kind of generalization is you can prove just from BK. You decompose nicely. And
Any other question? And maybe I have one short question.
Yeah.
So I guess the initial condition, it's very dependent on the points to be independent, right?
Sure.
So is there any class, like slightly more general class of initial conditions that we got?
right. So for this type of precision, absolutely not. This is really the most precise result in the whole literature. But for No. Okay. Okay, let's say slightly for very simple models. So for this particular model, not that I'm aware of, but if you take, okay, there's a vast generalization of this. So if you take, for example, the East model, which is very much related, or FA1F model, which I can tell you about more, but for those ones in one dimension, you can study more general initial conditions, but it's not very common. That's not really the type of problematic we look at. But yeah, thanks.
Okay, so let's thank Ivailo again.